Hey everybody, this lecture is on Chapter 20, the urinary system. Let's go over the general characteristics of the urinary system. The organs of the urinary system are the kidneys, ureters, urinary bladder, and the urethra. The kidneys filter blood and form urine. The ureters transport urine from the kidneys to the urinary bladder. The urinary bladder collects and stores urine, and the urethra conveys urine from the urinary bladder to outside of the body. Let's look at the functions of the kidneys. Kidneys contribute to homeostasis as excretory organs. They maintain the composition, pH, and volume of body fluids within normal limits. The kidneys remove metabolic wastes and substances present in excess, including foreign substances like drugs and their toxic metabolites. The kidneys secrete hormones that regulate specific metabolic processes. This is a view of the urinary system. You can see that the kidneys lead down the ureters, the bladder. That's how I remember them. Ureters go the bladder, and then the urethra is the exit out of the body, and it has the urinary meatus. So let's start with the kidneys. The kidneys are a reddish-brown, bean-shaped organ with smooth surface. They're about 12 centimeters long, 6 centimeters wide, and 3 centimeters thick in adults. The kidneys lie on both sides of the vertebral column in depression on the posterior abdominal wall. They are known as retroperitoneal, meaning that they are behind the parietal peritoneum, so they're not actually in the abdominal cavity. The left kidney is 1.5 to 2 centimeters higher than the right kidney due to the position of the liver. The kidneys are surrounded by a fibrous renal capsule made of collagen, adipose tissue called renal fat, and connective tissue, also collagen, called renal fascia. Remember, if you removed all cells from your body and only collagen was left behind, you'd still see a perfect outline of your organs and your tissues. Figure A shows the retroperitoneal nature of the kidneys, and you can see the parietal peritoneum in figure B and how the kidney is posterior to that. This also shows the renal fascia and the adipose tissue. Fascia is important because it binds the organs in their own little pockets throughout the body. Even muscles have fascia. A lot of times that's what hurts when you have bound muscles that needed massaged. So the fascia is like collagen strands that hold your organs in place. Pretty cool. Okay, we got a lot of things here in the kidney. There's that hilum again. Remember, the lungs had a hilum, and I told you the kidneys do as well. Those little beans. So let's take a look at the other structures. We've got a renal sinus, a renal cortex, a renal medulla, and a renal column. The hilum, the renal pelvis, the renal capsule, and nephrons. So if you haven't gathered, renal indicates kidney. So the renal sinuses are a hollow chamber in a medial depression. The renal cortex is the outer region of the kidney. The renal medulla is the inner region composed of the renal pyramids. The renal columns are extensions of the cortex that dip into the medulla. The hilum is the entrance to the renal sinus. The renal pelvis is the funnel-shaped sac, superior end of the ureter. It has the minor calyces, which are large tubes that merge to form the renal pelvis. Excuse me, that was the major calyces, or the large tubes that merge to form renal pelvis. And the minor calyces are small tubes that merge to form major calyces. The renal capsule is the fibrous capsule around the kidney. And then nephrons are functional units of the kidney, each of which is the site of urine production. So we see the renal capsule surrounding the entire kidney. And here's the renal cortex, kind of surrounding the body of the kidney. The renal medulla, it's like in the middle here, and it kind of looks like these fish tails, is what they look like to me. And then the minor calyx, which leads into the major calyx. And then here's the renal sinus. It's an opening. Here in the renal cortex, we have the start of our nephrons. And then in the renal medulla, we have a lot of our tubules. And so we're going to learn that there's renal tubules and all kinds of cool stuff in the nephrons. All right, here's another picture showing the aorta and the renal artery going in. And you can see the renal vein and the inferior vena cava here. And so this is a really good view of the hilum, which is that central little pocket where the arteries and veins enter and exit respectively. The kidneys have several functions. They regulate the volume and composition of body fluids. They remove excess water and electrolytes and metabolic waste from blood. They excrete waste in the urine. They secrete the hormone erythropoietin, which stimulates red blood cell production. They secrete the enzyme called renin, which helps to increase blood pressure. They produce the active form of vitamin D, calcitriol, which increases calcium absorption from the small intestine when blood calcium level is low. And when kidneys are not functioning properly, hemodialysis and continuous peritoneal dialysis can be used to filter wastes out of the blood. There are several major arteries of the kidneys. We have the renal artery, the segmental arteries, the interlobar arteries, arcuate or arciform arteries, and the cortical radiate arteries. The renal artery branches off the abdominal aorta and enters the kidney through the hilum. The segmental arteries branch off the renal artery. Interlobar arteries branch off the segmental arteries and flow between the renal pyramids. The arcuate or arciform arteries branch off interlobar arteries and arch around the renal periods. Cortical radiate arteries branch off arcuate arteries. Blood vessels within the nephrons. This is why the arteries are so important. So the afferent arteriole is a branch off the cortical radiate arteries, and each enters a different nephron. So this is how the blood is brought into the functional unit of the kidneys, which are the nephrons, in order to be filtered. All right, so the afferent arteriole is the branch off the cortical radiate arteries, each entering a different nephron. So now let's look at the glomerulus. The glomerulus is a capillary cluster that branches from the afferent arteriole, and it filters blood in each nephron. Efferent arteriole arises from the merging of glomerular capillaries, and it transports blood that was not filtered by the glomerulus. The peritubular capillaries branches off of the efferent arteriole and surrounds renal tubules. The venous drainage of the kidney includes as follows. From the nephron, the blood flows into the renal vein and leaves the kidney. Veins have the same name as their parallel arteries, such as the cortical radiate interlobar vein, the arciform vein, the interlobar vein, the renal vein. There are no segmental veins. Look at this blood vessels. That's incredible. Remember, each blood vessel goes to a nephron, and so the blood vessels are so full in the kidneys that even without any other tissue, you can still see the outline of the kidney with that blood vessels. Even the medullary pyramids and stuff like that. It's so amazing. Oh, these are little glomeruli. So this is a glomerulus here, the afferent arteriole that leads to the glomerulus, and then the efferent arteriole. And here's a flow chart of renal blood supply. I love these tables and charts that summarize everything. So we see the abdominal aorta goes to the renal artery, to the segmental artery, to the interlobar artery, to the arcuate artery, to the cortical radial artery, to the afferent arteriole. And the glomerulus is when it's actually like in the kidney. And then the efferent arteriole, or in the nephron, I should say, my apologies. And then we have the efferent arteriole, The peritubular capillaries or vasa recta goes to the cortical radiate vein, which then goes to the arcuate vein, or the peritubular capillaries go straight to the arcuate vein. Then the interlobar vein, no segmental veins, remember. Then the renal vein, and then the inferior vena cava. Wow. All right, so yes, I was thinking there was about 1 million nephrons in each kidney, and that's about right on the money. So there's about 1 million nephrons in each kidney. This is the functional unit of the kidney. And there are some animals out there that are so small that all they have are nephrons. They don't even have a kidney. They just have like a pair of nephrons in each little segment of their body, like an earthworm. So with us, though, we got to have a lot. So we got 100 million lot, or 1 million lot. So let's look at the two parts. We've got the renal corpuscle and the renal tubule. So the renal corpuscle is like a body, right? So it's the main body. And that's going to be the glomerulus and the glomerular or Bowman's capsule. The glomerulus is a capillary cluster. It filters blood to begin urine formation. It arises from the afferent arteriole and drains into the efferent arteriole. The glomerular or Bowman's capsule receives filtrate from the glomerulus. In the renal tubule, it extends from the glomerular capsule to the collecting duct. Filtrate proceeds from the glomerular capsule to the proximal tubule, to the nephron, to the loop of Henle, to the distal tubule. Distal tubules of several nephrons empty into a collecting duct. The collecting duct continues through the medulla and drains through the renal papilla into a minor calyx. This illustration shows the glomerulus and should be the glomerular capsule. Yep, there it is. And then we have the proximal tubule. Here we have blood flow towards the glomerulus through the afferent arteriole, and then away from the glomerulus through the efferent arteriole. These pedicels here help to increase the surface area of podocytes, which are going to be the visceral layer of the glomerular capsule, and they aid in the function of the glomerulus. Then here we see the nephron, so the glomerular capsule and the glomerulus, afferent arteriole, and then we have the proximal tubule, the loop of Henle, and then the distal tubule. Remember that proximal and distal means closer to or further from the attachment. And so in this case, it'd be closer to the attachment to the glomerulus or further away from the attachment of the glomerulus. So the proximal tubule is closer to the glomerulus. The distal tubule is the furthest away. Here's some illustrations of the renal cortex versus the renal medulla, and the glomeruli in the renal corpuscle and the collecting ducts in the renal medulla. You may have seen these images before when looking at tissues. The simple squamous epithelium is in the glomerulus, and then there's simple cuboidal epithelial in the collecting ducts. Woo! Here's the sequence of structures in urine formation. All right, so we've got the parts of the nephron and then the drainage system there. So it goes from glomerulus to glomerular capsule, proximal tubule, the descending limb of the nephron loop, the ascending limb of the nephron loop, distal tubule, collecting duct, minor calyx, major calyx, renal pelvis, ureter, urinary bladder, urethra. All right, here we are at the two types of nephrons in the kidneys. There's cortical nephrons and juxtamedullary nephrons. The cortical nephrons make up the majority of nephrons. 85% of nephrons are cortical nephrons. They lie almost completely in the renal cortex. They have short nephron loops, and their renal corpuscles are located near the surface of the kidney. In the juxtamedullary nephrons, they are a smaller percentage of nephrons, about 15% of the nephrons. They have long nephron loops that extend deep into the medulla. Renal corpuscles lie deep in the renal cortex, and they are important in regulating water balance and urine concentration. We have a juxtaglomerular apparatus, which is a structure that regulates the secretion of the enzyme renin. It monitors and adjusts blood pressure and sodium chloride content of the filtrate. It's found at the point of contact where ascending limb of the nephron loop passes between the afferent and efferent arterioles. At this point of contact, cells of both structures are specialized. We have the macula densa, which is tall, closely packed cells of the ascending limb, and this monitors sodium chloride content of the filtrate. In the juxtaglomerular cells, large vascular smooth muscle cells of afferent arteriole monitor blood pressure. This picture shows the juxtaglomerular apparatus. You can see the macula densa and the juxtaglomerular cells. And that is going to be doing sodium chloride content monitoring in the macula densa and blood pressure in the juxtaglomerular. And so this is important because we need to conserve sodium chloride, but we also need to make sure we excrete enough so that our blood pressure doesn't get too high. And you'll learn that diabetes damages your kidneys because as the blood pressure rises, it can scar the glomerulus, and then the blood pressure has to get higher to squeeze more blood into the narrowed arteries that have been scarred, which then further scars them, and that's a positive feedback loop that can lead to kidney disease. And so this is a very important area of the kidney for sodium chloride maintenance and blood pressure maintenance in the kidneys. So glomerulonephritis is going to be the inflammation of the glomeruli. Nephritis, as you can see, is inflammation of the kidney. And so with glomerulonephritis being the inflammation of the glomeruli, it can be acute or chronic. If it's acute, it results from an abnormal immune reaction 1 to 3 weeks after infection by beta hemolytic streptococcus. Ooh, that's that strep throat that eats up your throat tissues. The antibody thus the infection does not start in the kidney. The antigen-antibody complexes form insoluble immune complexes, which lodge in the kidneys. Complexes deposit in and block glomeruli. In chronic glomerulonephritis, it's a progressive disease. It involves prolonged inflammation. More and more nephrons are damaged until the kidneys cannot function. Fibrous tissue replaces glomerular membranes, disabling the nephrons. Let's talk about urine. Urine is the excretory product formed by nephrons and collecting ducts, as they regulate the composition of body fluids and remove waste from the blood. Urine contains wastes, excess water, and electrolytes. There are 3 processes of urine formation: glomerular filtration, tubular reabsorption, and tubular secretion. With glomerular filtration, it's performed by specialized glomerular capillaries in the first capillary bed. Water and small molecules are filtered. Filtered fluid enters renal tubules and becomes tubular fluid. During tubular reabsorption, the transfer of filtered substances from renal tubules to peritubular capillaries, which is the second capillary bed, only reclaims useful substances, while waste continues to become urine. In tubular secretion, the transfer of certain substances from peritubular capillaries to renal tubules adds waste products and excess substances to forming urine. So here we can see the specialized capillaries of the kidney, and we've got tubular reabsorption and tubular secretion in the peritubular capillaries. So let's look at glomerular filtration. It's the first step of urine formation. Substances move from the blood in the glomerulus into the glomerular capsule. Water and small dissolved molecules and ions can be filtered. Large molecules, such as proteins, remain in the blood due to their large size. That's why if you have protein in your blood, that's a bad sign. Glomerular capillaries are much more permeable than other capillaries due to fenestra, which are tiny openings in the walls. Glomerular filtrate is formed as substances filter from the glomerulus into the glomerular capsule. Filtrate has about the same composition as your tissue fluid. So this shows the glomerular capsule and the glomerulus. And it's going to go down into the proximal tubules. Oh, here's the fenestra, which are the pores that allow for the capillaries to be more permeable. Filtration pressure is the main force that filters substances through the glomerular capillary wall, and it is the hydrostatic pressure of the blood of the glomerulus. Afferent arteriole has larger diameter than efferent arteriole and others in the body. Resistance in efferent arteriole increases blood pressure in the glomerulus, which favors filtration. Net filtration pressure equals force favoring filtration minus forces opposing filtration. Force favoring filtration is the glomerular capillary hydrostatic blood pressure, aka blood pressure. Forces opposing filtration, the glomerular capillary colloid osmotic pressure, due to plasma proteins in the glomerulus, and capsular hydrostatic pressure. As long as the net filtration pressure in the glomerulus is positive, filtration will occur. So this shows the filtration pressure and the glomerular hydrostatic pressure, which we know as blood pressure. Coming outward, force is positive 60 millimeters. Usually we measure pressure in millimeters per mercury. The inward force of plasma colloid osmotic pressure is negative 32 millimeters. And then capsular hydrostatic pressure, inward flow, is negative 18 millimeters of mercury of pressure. So net filtration pressure is about 10 millimeters of mercury. Glomerular filtration rate. Kidneys receive 25% of the cardiac output. 20% of the blood is filtered by glomerular capillaries. The average adult glomerular filtration rate is about 125 milliliters a minute or 180 liters a day. The blood plasma is filtered about 60 times a day. Only a small percentage of the filtrate is actually excreted as urine. Factors affecting glomerular filtration rate. Glomerular filtration rate is directly proportional to the net filtration pressure. So anything that changes the net filtration pressure will change the glomerular or capsular hydrostatic pressure or the glomerular colloid osmotic pressure. The changes in diameter of afferent or efferent arterioles also affect the glomerular filtration rate. This shows the 180 liters, which is going to equate to 45 gallons of blood a day, as compared to the 0.6 to 2.5 liters of urine produced per day. Autoregulation keeps the glomerular filtration rate relatively constant. Increase in the systemic blood pressure causes vasoconstriction of the afferent arterioles. It reduces blood flow to the glomerulus, decreases the glomerular filtration rate, and maintains kidney function. The juxtaglomerular apparatus and tubuloglomerular feedback increased glomerular filtration rate increases the amount of filtrate in renal tubules. When excess sodium chloride reaches the macula densa in the distal tube of the juxtaglomerular apparatus, afferent arterioles are vasoconstricted. The glomerular filtration rate is decreased towards normal range. Certain conditions may increase or decrease the glomerular filtration rate in order to maintain homeostasis, such as when the glomerular filtration rate increases in response to excess body fluids. Hormonal control by cardiac hormones. The heart secretes atrial natriuretic peptide and ventricular natriuretic peptide in response to increased blood volume and pressure. The increased excretion of sodium and water excretion occurs as a result. The sympathetic nervous system exerts neural control over glomerular filtration rate. Sympathetic responses to change in systemic blood pressure also affect the kidneys. When blood pressure or volume decreases, Sympathetic stimulation causes afferent and efferent arterioles to constrict simultaneously. This maintains the glomerular filtration rate in normal range. The hormonal control via the renin-angiotensin-aldosterone system. This is also called the renin-angiotensin system. It is activated by decreased blood pressure, sympathetic stimulation, or macula densa. The decrease in sodium chloride concentration causes the secretion of renin. Renin converts angiotensinogen to angiotensin 1, which is converted to angiotensin 2 by ACE. Angiotensin 2 causes vasoconstriction of afferent and efferent arterioles and the secretion of the antidiuretic hormone and aldosterone. This increases thirst, the retention of sodium water, and blood pressure. A shows decreased glomerular filtration rate and says vasoconstriction of the afferent arteriole decreases the filtration pressure and the glomerular filtration rate. Figure B shows increased glomerular filtration rate. Vasoconstriction of the efferent arteriole increases net filtration pressure and glomerular filtration rate. Figure C shows a slight decrease in the glomerular filtration rate. Vasoconstriction of both afferent and efferent arterioles combines the effects of A and B. Net filtration pressure decreases, but not as much as it would in response to afferent and arteriolar constriction alone. Figure D, we see increased glomerular filtration rate. Vasodilation of the afferent arteriole increases the net filtration pressure. The renin-angiotensin system. So we see that the liver secretes the angiotensin, the kidney secretes the renin, and this is going to help it be converted into angiotensin 1. Angiotensin converting enzyme, which is ACE, helps to convert the angiotensin 2, and this leads to vasoconstriction, increased aldosterone secretion, increased antidiuretic secretion, and increased thirst. Now let's look at tubular reabsorption, the movement of useful substances from the renal tubules back into the blood of peritubular capillaries. Most tubular reabsorption, 70% of it, occurs in the proximal tubule, which is lined with microvilli. Different parts of the renal tubule reabsorb specific substances. Substances are transported by various methods of transport. We have diffusion, which is the passive transport of lipid-soluble substances, the passive transport through ion channels or carriers, and osmosis, which is the passive transport of water, sometimes containing solutes. In active transport, the movement of substances against their concentration gradients requires ATP. It has limited transport capacity due to the number of carrier proteins. Each substance has a transport maximum. It can only transport a specific number of molecules in a certain amount of time. The renal plasma threshold is reached when there is more transported substance in the plasma than the active transport mechanism can handle. The excess spills into forming urine. Substances that are reabsorbed by active transport are glucose, amino acids, lactic acids, citric acids, and phosphate, sulfate, calcium, potassium, and sodium ions. So remember I said proteins going into the urine is usually a sign of problems. Another sign of problems is glucose in the urine. That can indicate diabetes. You should be able to reabsorb your glucose back into your bloodstream. Only if it's at the transport maximum will you lose it into your urine. The nephrotic syndrome, a set of symptoms that occur in people with renal disease. Some renal disorders cause increased permeability of glomerular membranes, which allows plasma proteins to enter the urine. The loss of plasma proteins into the urine causes widespread edema and an increased likelihood of infection. Increased concentration of plasma proteins decreases the osmotic pressure, leading to edema, ascites, and fluid accumulation in several body cavities. Edema and other abnormal fluid accumulation leads to a decrease in blood volume and pressure. These events lead to activation of renin-angiotensin system and ADH and aldosterone secretion. Kidneys conserve sodium and water, which restores blood volume, but makes the edema worse. So the influx of sodium. So sodium and water reabsorption. About 70% of the sodium ions are reabsorbed in the proximal tubule by active transport. In sodium active transport, providing energy and the method for reabsorption of many nutrients, including glucose, amino acids, ions, vitamins, and water. The sodium-potassium pumps create a gradient that provides for reabsorption by secondary active transport. Sodium diffuses down its concentration gradient. Other substances are co-transported by carrying proteins into the epithelial cells of the renal tubule. Glucose and negatively charged ions are reabsorbed by this method. The process continues throughout the renal tubules. About 97 to 99% of sodium and water are reabsorbed before the excretion of urine. Antidiuretic hormone increases water reabsorption, and aldosterone stimulates sodium reabsorption. This summary table shows the averages values for sodium and water filtration, reabsorption, and secretion. And this figure shows the sodium and the water reabsorption. Let's look at tubular secretion. Tubular secretion is the reverse of tubular reabsorption. The movement of substances from plasma of peritubular capillaries into the fluid of renal tubules. Substances are derived from 80% of the plasma is not filtered by glomeruli, waste, and large molecules. Remember, of those 180 liters that get filtered every day, only like less than 3 liters get urinated out of our body. So active transport mechanisms function in tubular secretion, but they work in the opposite direction as tubular reabsorption. Substances secreted into forming urine include drugs, ions such as potassium, and hydrogen ions. The secretion of hydrogen ions is important in regulating the pH of body fluids. Potassium ions are secreted as hydrogen ions are reabsorbed in the distal tubule. My apologies. This illustration shows the tubular secretion of potassium ions out of the collecting duct. The hormones aldosterone and cardiac natriuretic peptides affect solute concentration of urine, particularly sodium. The ability of kidneys to maintain internal environment depends mainly on their ability to concentrate urine by reabsorbing large amounts of water. The distal tubule and collecting duct cells are impermeable to water in the absence of antidiuretic hormone, so water may be excreted as dilute urine. If antidiuretic hormone is present, those segments become permeable and water is reabsorbed by osmosis into hypertonic medullary interstitial fluid. The urine becomes very concentrated and the urine volume decreases. Although the majority of nephrons are cortical, juxtamedullary nephrons are more important in the regulation of water reabsorption. Figure A shows low antidiuretic hormone, and you can see that we've got dilute urine, so we're removing lots of water, versus high antidiuretic hormone, which means that we are reabsorbing water back into the bloodstream and we're thus making concentrated urine. This table is going to compare when the body fluids are too concentrated versus body fluids too dilute. There's a countercurrent mechanism in the nephron loops of the juxtamedullary nephrons, which keeps medullary interstitial fluid hypertonic, so a concentrated urine is produced. Ascending and descending limbs of nephron loops are parallel, and in close proximity to each other they work together. The thick ascending limb of the nephron loop is impermeable to water, but actively resorbs sodium and chloride ions. This results in hypertonic interstitial fluid and hypotonic tubular fluid in the ascending limb. In response, water in the descending limb leaves by osmosis since it is permeable to water but not sodium and chloride ions. This results in hypertonic tubular fluid in the descending limb. The mechanism is called the countercurrent multiplier because every time the cycle is completed, the sodium chloride concentration in the ascending limb increases. The vasa recta of the juxtamedullary nephrons also have a countercurrent mechanism called a countercurrent exchanger since no active transport occurs. This illustration shows the countercurrent multiplier, and then it shows that the increasing sodium chloride concentration in the medullary interstitial fluid, we have the descending limb permeable to water, and so that's hypertonic fluid, meaning that it's going to be high concentrations of salt. And then we have the medullary interstitial fluid, and then here's the thick ascending limb, which is impermeable to water, but we're going to be able to take out sodium and chloride. And then we have hypotonic fluid, which will be mostly water. So we've conserved our precious salts. And then this shows the countercurrent mechanism of the vasa recta, which is going to be reabsorbing the sodium chloride as needed. So figure 20.3 shows the functions of nephron components and the collecting duct. Now let's look at urea and uric acid excretion. Urea is a byproduct of amino acid catabolism. It has plasma concentration reflecting the amount of protein in the diet. It enters the renal tubules through glomerular filtration and undergoes both tubular reabsorption and tubular secretion. Up to 80% is reabsorbed and the rest is excreted in the urine. Uric acid is a product of nucleic acid metabolism. It enters the renal tubules through the glomerular filtration. Active transport completely reabsorbs filtered uric acid. About 10% of uric acid enters urine through the tubular secretion and is excreted. The excess uric acid may lead to a painful condition called gout, in which uric acid precipitates in the blood and forms crystals in the joints. Urine composition reflects the volumes of water and solutes that the kidneys must excrete or conserve to maintain homeostasis. The composition of urine varies due to dietary intake and physical activity, but typically it consists of about 95% water. It contains metabolic waste products such as urea, uric acid, and creatinine. It contains small amounts of amino acids and varying amounts of electrolytes. Urine volume is about 0.6 to 2.5 liters per day. 50 to 60 milliliters of urine output an hour is normal. The volume varies with fluid intake, sweating, body temperature, emotional state, and environmental factors. This table, 20.4, shows the relative concentrations of plasma, glomerular filtrate, and urine components. Renal clearance is the rate at which a chemical is removed from the plasma by the kidney. Tests indicate kidney efficiency, glomerular damage, progression of renal disease. Renal clearance tests look for inulin, a polysaccharide of some plant roots, the creatinine clearance test, and since these substances are both filtered by the glomerulus but neither reabsorbed nor secreted, tests of renal clearance are used to calculate glomerular filtration rate. The storage and elimination of urine. Urine forms throughout the nephrons and collecting ducts and then follows this pathway to the outside of the body. It goes through openings in the renal papilla, drains into the minor calyces, drains into the larger major calyces, drains into the renal pelvis, follows the renal pelvis, which narrows to become the ureter, is transported to the urinary bladder for storage, and leaves the body through the urethra. The ureters are tubular organs about 25 centimeters long, which transports urine from the kidney to urinary bladder. Each begins as a renal pelvis in the kidney. Each empties into posterior portion of the urinary bladder in the pelvic cavity. The wall of the ureter consists of 3 layers: the inner mucous coat, the middle muscular coat, and the outer fibrous coat. The inner mucous coat, or mucosa, consists of transitional epithelium You've noticed that each of these organ systems that we talk about, where the organ is open to the outside, the inner lining is the mucous membrane. Then we have a middle muscular coat, which is the muscularis, and then the outer fibrous coat, or adventitia. Peristaltic waves transport urine along the ureters. An obstruction such as a kidney stone or renal calculus in a ureter causes strong peristaltic waves in the obstructed ureter to move the stone towards the urinary bladder. The uroretrorenal reflex constricts renal arteries and decreases urine production in the affected kidney. Figure 20.26 shows a cross-section of a ureter, and you can see the inner mucosal lining, middle muscular lining, and then the outer fibrous coat. Chronic kidney disease, or chronic glomerulonephritis. This is the inflammation of the glomerular capillaries. It's a progressive degenerative disease with no cure. Symptoms include hypertension, proteinuria, hematuria, dark urine, elevated blood levels of blood urea nitrogen, or BUN, and creatinine, decreased protein in the blood. This can lead to end-stage renal disease. Treatments are hemodialysis 3 times a week and kidney transplant. Kidney stones can be composed of uric acid, calcium oxalate, calcium phosphate, or magnesium phosphate. They form in the collecting ducts or the renal pelvis of the kidney. Causes severe pain, nausea and vomiting, and blood in the urine. 60% of kidney stones pass on their own. Others can be shattered with lithotripsy or removed surgically. The tendency to form kidney stones is inherited, especially calcium stones. Causes are calcium supplements in those with the inherited tendency, excess vitamin D, urinary tract blockage, and urinary tract infections. The urinary bladder is a hollow, distensible muscular organ in the pelvic cavity. It stores urine and sends it to the urethra. It contacts the anterior walls of the uterus and vagina in the female and lies posteriorly against the rectum in the male. The triangular trigon at the floor of the bladder contains openings at each of its 3 corners, 2 for the ureters and 1 for the urethra. The wall consists of 4 layers: the inner mucosa coat, called the mucosa transitional epithelium, a submucous coat, the submucosa, a muscular coat, the muscularis, and an outer serous coat called the serosa, the upper surface only. Smooth muscle fibers of the muscular coat comprise the detrusor muscle. An internal urethral sphincter surrounds the neck of the bladder. This shows the bladder contacting the so funny. The uterus. I totally blanked for a second. The uterus and the vagina. I'm like, ureter. Oh my lord. Okay. And then here's in the male where you've got the prostate and the vas deferens going over the bladder. This shows the trigon, so pretty, with the opening of the ureters and then the urinary urethra. And then there's the prostate gland, so this is the male bladder. And then this is showing the seminal vesicle and the prostate gland with the muscular linings underneath it. And the serosa, which is the peritoneum in this case. And then this shows the micrograph of the urinary bladder. So we've got the mucosa on the internal lining, and then the submucosa superficial to that. So we're moving towards the surface of the organ, and then the muscularis. So the lining of the hollow organs is like the innermost part, and the lumen is that space. And then as we move towards the outer wall of the organ, that's when we get into the muscularis and the outer connective tissues. The urethra is a tubular organ that conveys urine from the urinary bladder to the outside of the body. It is the innermost mucosa coat and thick muscular coat, and it has an internal urethral sphincter and an external urethral sphincter. The internal sphincters are usually involuntary, and so they contract without your conscious awareness. And then the external sphincters are voluntary, and so you can actively control those, which is good. So you can hold in your urine if you need to. And then we have the submucous coat, or submucosa, that has many mucous glands, and they're called urethral glands. The female urethra is about 4 centimeters long. It's an external urethral orifice is anterior to the vaginal opening. The male urethra is about 19.5 centimeters long, has a dual function for both urination and reproduction. It has three sections: the prostatic urethra, the membranous urethra, and the spongy urethra. So this shows the urethra here with the mucosa on the inner lining. The lumen is the center, and then the muscularis and the urethral glands. In micturition, that is the expulsion of urine from the urinary bladder. Urine leaves the urinary bladder through the micturition reflex, which is an autonomic reflex. It occurs through the reflex contraction of the detrusal muscle and the reflex relaxation of the internal urethral sphincter. It requires relaxation of the external urethral sphincter, which is voluntary. The urinary bladder may hold as much as 600 milliliters. The urge to urinate starts when it contains about 150 milliliters. It is controlled by the micturition reflex center and sacral spinal cord. Problems with micturition include incontinence, which is the inability to control micturition, and nocturnal enuresis, which is bedwetting. Another interesting thing with micturition is that if the bladder is distended, meaning full, and the patient has a spinal cord injury, sometimes it can lead to autonomic dysreflexia, particularly in the first year after the spinal cord injury. And this is a very scary spike in blood pressure. Table 20.5 shows the major events of micturition. And here you can see where it's an autonomic impulse, where we have the parasympathetic nervous system in control. And so if the sympathetic nervous system overreacts as a result of the paralysis, then that's when the autonomic dysreflexia can occur, causing a spike, in blood pressure. Figure 20.6 shows developmental abnormalities of the urinary system. We have crossed fuse ectopia, horseshoe kidney, nephrotic syndrome, oligomeganephronia, polycystic kidney disease, renal agenesis, renal dysplasia, renal hypoplasia, tubular dysgenesis, and vesicuratorial reflux. Urinalysis, clues to health. So urinalysis can be used to diagnose certain diseases or disorders and check for drug usage. For example, people with untreated diabetes mellitus have glucose in their urine. There are several harmful inherited disorders that alter the urine color and sometimes the viscosity. Some genetic conditions alter urine without causing harm. Beeturia, in which the urine turns pink after eating beets, and urinary excretion of odoriferous component of asparagus. I've heard rumor that we all have that odoriferous condition after eating asparagus. What's genetic is our ability to smell it, but I could be wrong. All right, so finally, lifespan changes. The urinary system has sufficient reserve in both structure and function to mask age-related changes. Kidneys become slower to remove nitrogenous waste and toxins and to compensate for changes that maintain homeostasis. Age-related changes include kidneys appear scarred and grainy due to connective tissue accumulation, kidney cells die, and by age 80, the kidneys have lost a third of their mass. Kidney shrinkage is due to the loss of glomeruli, the loss of surface area for filtration decreases the glomerular filtration rate to about half by age 75. Proteinuria may develop, renal tubules thicken, the reabsorption of nutrients and ions becomes less efficient, it's harder for the kidneys to clear certain substances, blood flow to the kidneys slows, the urinary bladder, ureters, and urethra lose elasticity, the bladder holds less urine, kidneys are less able to activate vitamin D, and a loss of bladder control may result in incontinence. Oh boy. All right, well, hey, the alternative is death, so I'd rather have my kidneys just do less than do nothing at all, right? So anyway, have a great day. Thanks for listening.